Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss Taylor series. Let's begin. When a complex function is analytic within a circle, then that function can be expanded by using Taylor series. But if that given function is not analytic within that circle, then that function is expanded by using Lorentz series. In this video, we discuss about Taylor series, and in upcoming video that based upon Lorentz series. So, stay tuned with this particular channel. Taylor's theorem statement: if a function f of z is analytic at all points inside a circle C, and that circle with its center at point A and radius r, then at each point z inside that circle C is expanded as f of z is equal to f of a plus f dash a, first order differentiation at point A, z minus a plus f double dash a divided by 2 factorial z minus a square plus up to nth order differentiation of that function at a divided by n factorial z minus a to the power n plus dot dot dot. Look at that series. Here that function means it is 0th order differentiation and divided by 0 factorial. At that point it has first order differentiation divided by 1 factorial z minus a up to the differentiation order increases. Here 0th order differentiation, first order differentiation, second order differentiation, and so on up to nth order differentiation, 0 factorial divided by 1 factorial divided by 2 factorial up to n factorial. Here z minus a to the power 0, here z minus a to the power 1, z minus a to the power 2 up to z minus a to the power n. In this way we expand that given complex function by using Taylor's theorem. Let us prove that Taylor's theorem. As it is given a closed curve C, that is not closed curve, that is a circle. Center at point A and its radius as capital R. We take any point z inside C, take a point z here, that is within that C. Now draw a circle C1 with center at A enclosing the point Z. That is the point Z. So, I draw a circle named as C1 that encloses the point Z. Let we take another point let W be a point on the drawn circle C1. W is a point in that of drawn circle C1. So 1 divided by W minus Z can be written as 1 divided by W minus A plus A minus Z. Add and subtract A. 1 divided by W minus A minus Z minus A. Taking W minus A as common, 1 divided by W minus A as common, we have 1 minus Z minus A divided by W minus A, which is equal to 1 divided by W minus A, 1 minus Z minus A divided by W minus A to the power minus 1. It can be expanded binomially. Applying binomial theorem, expansion of that term using binomial theorem, 1 divided by W minus A, 1 plus Z minus A divided by W minus A plus Z minus A divided by W minus A square plus dot 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 up to Z minus A to the power n divided by W minus A, sorry, Z minus A divided by W minus A to the power n plus dot dot dot. Here 1 by W minus A is multiplied within that of bracket term. So we have 1 divided by W minus Z is equal to 1 into that term, 1 divided by W minus A plus Z minus A divided by W minus A whole square plus Z minus A square divided by W minus A Q plus dot 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 up to Z minus A to the power n divided by W minus A to the power n plus 1 dot dot dot, and equation number 1. As in that of figure, that point Z within that of circle C1, therefore the magnitude of Z minus A must be less than the magnitude of W minus A, as Z point is within that of circle C1 and W point on the circle C1. W Z minus A magnitude divided by W minus A magnitude less than 1. That particular series converges uniformly show the series converges uniformly hence that series is integrable, as that term w minus a divided by w z minus a magnitude divided by w minus a magnitude less than 1. So, that series is converges and that series can be integrable, hence the series is integrable. How to integrate that series? Let me multiply f of w in equation 1. Now, multiply f of w in equation 1. It is written like this: f of w divided by w minus z is equal to f of w divided by w minus a plus z minus a f of w divided by w minus a square plus z minus a square f of w divided by w minus a whole cube plus dot 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 up to nth term. In nth term, z minus a to the power n f of w divided by w minus a to the power n plus 1 dot dot dot. Now, integrate it. On integrating, with respect to w, we integrate it within that closed curve C1. The integrals are written closed curve integration over C1 f of w divided by w minus z with respect to w, means we have dw is equal to closed curve integration over C1 f of w divided by w minus a dw plus z minus a closed curve integration over C1 f of w divided by w minus a square dw plus z minus a square closed curve integration over C1 f of w divided by w minus a whole cube dw plus dot 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 nth term. As nth term, we write z minus a to the power n closed curve integration over C1 f of w divided by w minus a to the power n plus 1 dw plus dot dot dot. That is equation number 2. Look at that equation. That term f of w divided by w minus z dw can be written as 2 pi I f of z by using Cauchy's integral formula. As we know that closed curve integration over C1 f of w divided by w minus z dw, that results 2 pi I over that function f of z. That we get from Cauchy's integral formula. And again that type of integral results closed curve integration over C1 f of w divided by w minus a dw, similarly 2 pi I at f of a, and also the closed curve integration over C1 f of w divided by w minus a square dw, that type of integral, square, cube and so on. We study about the derivative of analytic functions. So, here we prefer it as 2 pi I faster differentiation at a and so on, and so on. It proceeds. For cube we have 2 pi I divided by 2 factorial and f dash n, that is the differentiation of analytic functions by using Cauchy's integral formula. These substitutions now we have to put in equation number 2. Substituting these values, in equation 2, we have here 2 pi I and all these terms contain 2 pi I. In that of RHS side we take 2 pi I as common, and 2 pi I on left hand side and 2 pi I on RHS side are cancelled out. So, we have that integral written as f of z. F of z is equal to that integral as f of a plus here z minus a into f of a, z minus a into that integral term, that is f dash a. So, f dash a z minus a plus f double dash a divided by 2 factorial z minus a square up to nth term f nth a divided by n factorial z minus a to the power n plus dot dot dot. The expansion of that given function by using Taylor's theorem. There are a special case when we evaluate that series at a is equal to 0. If a is equal to 0, then the series becomes f of z is equal to f 0 plus z f dash at 0, means we evaluate that series at origin, plus z square divided by 2 factorial f double dash 0 plus dot 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 z to the power n divided by n factorial fn 0. That type of series when we evaluate at origin is named as the Maclaurin series. This series is known as Maclaurin series. Maclaurin series. When we expand that series at origin, the Taylor series convert into Maclaurin series. So here we state the Taylor's theorem and its proof. This is a Taylor's theorem expansion, and when we expand the Taylor's theorem at origin, that series is basically known as the Maclaurin series. Now we solve two questions by using Taylor's theorem. Question number 1, expand e to the power z about a. Solution. Here we have f of z is equal to e to the power z. Therefore, f of a, similarly e to the power a, its first order differentiation f dash z is equal to e to the power z, which implies f dash a is equal to e to the power a. Second order differentiation f double dash z is equal to e to the power z. At point A, same e to the power a, up to it continued. For nth order differentiation f n z e to the power z, at that point f n a is equal to e to the power a. By Taylor series of that function, by Taylor series of f of z, now expanded as f of z at f of a plus z minus a f dash a plus z minus a square divided by 2 factorial f double dash a plus dot 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 f dash z, that is e to the power z, f of a e to the power a plus z minus a divided by 1 factorial e to the power a plus z minus a square divided by 2 factorial e to the power a plus dot dot dot. That is the expansion of that given function about the point A. Next question, expand f of z is equal to 1 divided by z about z is equal to 2 in Taylor's series. Solution. Here we have that function f of z is equal to 1 divided by z. Therefore, the first order differentiation f dash z is equal to minus 1 divided by z square. Second order differentiation f double dash z is equal to 2 divided by z cube, up to nth order differentiation minus 1 to the power n factorial divided by z to the power n plus 1. Let me expand it by using Taylor's series. by Taylor series, that given function f of z is expanded as f of z is equal to 2. So, f of 2 sorry a is equal to 2, f of 2 plus z minus a sorry z minus 2 f of 2 plus z minus 2 square divided by 2 factorial f double dash at 2 up to z minus 2 to the power n divided by n factorial fn 2 plus dot 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 at f of 2, that is 1 by 2, 1 divided by 2 plus z minus 2, here f dash 2, so f dash 2 minus 1 by z square, so minus 1 divided by 2 square plus z minus 2 square divided by 2 factorial f double dash at 2. In place of z we substitute 2, so we have 2 divided by 2 to the power q, 2 divided by 2 to the power cube plus dot 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 up to nth term z minus 2 to the power n divided by n factorial minus 1 to the power n factorial divided by 2 to the power n plus 1 dot dot dot. It is solved as 1 by 2 minus 1 by 4 z minus 2 plus 1 by 8 z minus 2 square minus dot 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 plus minus 1 to the power n divided by 2 to the power n plus 1 z minus 2 to the power n. That is the required expansion of the given function f of z, as f of z is equal to 1 by z, which is equal to 1 by z. F of z is equal to 1 by z, that expansion using Taylor's theorem at z is equal to 2. At z is equal to 2, we expand that given function by using Taylor's series. So, with the help of this video lecture, we understand what is Taylor's series, its statement, and we have to prove the Taylor series by using some techniques. That is the Taylor series expansion. If we evaluate the Taylor series at origin, that becomes a new type of series which is known as the Maclaurin series. Questions related to Taylor series, we expand that given function by using Taylor series. So, with this useful and informative notes, let me wind up this session. Thank you.